Hi everybody, Jim Kelly back again, and I'm getting ready to build my Nervo cards for my robot. Uh, Ralph is his name, and so I started out right here on the eMove homepage, and I looked up the tutorial on how to do that. Yeah, but it didn't quite satisfy me. It's not bad material. You can, of course, build it based on just nothing but Gail's tutorial, but it didn't satisfy my need to know why. I don't work well if I just follow solder here, solder there, solder here. The why always gets in the way for me. So I got out my continuity checker and went through some things to satisfy it that need to know why. And so I checked around on the board and found where several of the connections were made. And I thought maybe it might be just fun and help maybe somebody else satisfy their curiosity about why the board is the way it is. So I decided to make a video about it. Let's take a look at how I got things started first. First, you can go to the shop, which is the store. Okay, remember this is a French site translated to English. So shop is store, and you have two options in here for buying the Nervo boards. You can either just buy the boards and then use the bill of materials and buy your own components, or you can buy the board with the components, which is the route I elected to choose. So when my parts came in, I then went to from the home page, I went to Nervo board tutorial, looked it up. Here we go, and his tutorial begins. The first thing that he says in the tutorial is, whoops, there's a mistake on the old boards. However, he doesn't sell the old boards anymore, so you can kind of skip over that material. The only thing that you might remember is that if you're using the Uno board instead of the Mega board, you still have to do that cut line and cut off the extra part that the Uno doesn't support. Other than that, you can skip on down to step one. Okay, step one, he starts the actual build. Now, I went through here and, and read it and figured things out, and everything looks good. It works. It will get the board built. But like I said, I needed to know why. So I'm not going to go down through here and compare step by step. It's available. You can read through it. Then you can look at my video and see the differences. And hopefully the two overlap in such a way that they fill in all the gaps for you. So with that said, let me pop up here and get things started. And the first thing I did was start from the very end. So let me get everything started back here from the very beginning. There we go. First shot. So I'm going to shrink myself down, get out of the way here a little bit. And this is what you'll get now. Instead of the green cards that come as all one assembly, and you used to have to cut these boards out from that one assembly. Now he ships them as individual cards, so you no longer have to do all that separation. And so this is what comes in the package. And this is how I'm going to kind of step through my tutorial complement. Let's call it that. I'm not replacing his tutorial. I'm just complementing it. So I'm going to focus first on servo power, analog voltage selection, the AREF, and I'll go through what all this is, and he does a little bit in his tutorial too. The SIP resistor, what role it plays for you, and how to power up the PIR detector, the optional LEDs, and then the ribbon cables. And I'm not going to go through his part of the tutorial where he shows you how to mount the mini breakout boards around in different places in the robot. I'm not that far along. I couldn't even begin to compare my way to his way. So just know that he still gives you a good guideline on where to mount the boards. So that's it. Let's get started. Servo power. Servo power is provided by external power links to the board, and you can have from 1 to 3 different power links. So he's divided the board up into those 3 sections. One power connector here, another here, and another here. So you can put different powers for your servos depending on the servos that you elect to use. But like him, I bought the same servo systems that he recommends. They all run fine on 6 volts. So he provides a jumper method that allows you to jumper all of these individual servo powers to 1. And basically what he tells you is that I'm going to show you that the board, this power connection right here, powers this section of the board. Okay, and so if you look at this plus and minus here, this plus and minus power going out to your servos comes from these 2 connections, plus and minus here. This section of the board, the plus and the minus, is fed from this connector, plus and minus. And over here, this connector feeds this section of the board. Now, if we want to use just one power supply, he gives us a method to do the jumping. So I took my continuity meter, and this connector reads to this point. Okay, and this connector reads to this point. This connector reads to this point. And the grounds, all the grounds on here are common. So this ground, and this ground, and the grounds coming in from the board are all tied common. So the only thing we need to do the jumper on is the positive side, the power side. So if you solder a jumper here, you no longer have to put a power source here, because this side is now jumpered to this connector. Now, if you solder this connector, you no longer have to put power source here. So basically what we're saying is, if you elect to use one power source, use this connector, and jumper, and jumper. And that will provide power to all 3 sections. Now, I say you can use the center one as the only one. Truth is, once you put these jumpers in, you could pick any one of these to put your power connector on, and it'd work just fine. He points out that on one of his 2 boards, since he built the whole robot, you'll need 2 of these boards, right? On one side, he put 2 connectors in. One, he actually brings the power into the board. The other he uses as a convenient way to jumper to the other board. so that he can use one connection, one power supply connection, and just jumper to the other board. There is one little tricky thing that I discovered here, that if you miss it, half of something won't work, okay? And I showed you here how you can bring power into this board, and that this would replace this connector, and you wouldn't need to put a power source here. But when you do that, this puts positives and negative here, but it only does it for, it puts positive here for 1, 2, 3, 4 of these power connectors. These will read open or dead, no power to them. And so will this positive connection here. Now, I don't understand what option he was maybe thinking of in the future or something, but those are dead. And the only way to make those hot is to jumper this connector right here. When you power that up, then these become hot and active, and so this side becomes fully powered. I don't know why he did that, but that's what happens if you don't, so remember that this side needs actually both jumpers right here done in order to give full power up and down this strip. That's it. That's servo power in a nutshell. So now let's take a look at the analog voltage selection. From the card, from the Mega card, we have a power section down here. And we have 3.3 volts, we have 5 volts, and we have ground connectors. Those are brought up through these pins onto our shield that we're building. Okay, and here on our shield, those power connections are brought up right over here. 3.3 volts, 5 volts, and ground. Now, we're not going to talk much about the ground because, as I pointed out during power, servo power, these grounds are everywhere. They're tied common with servo power. Everything is tied common, which is the best practice when you're using multiple sources of power. But what we're going to focus on here is the 3.3 volts or the 5 volts. And what we have is an option to feed our analog power, the plus strip right here, and this plus strip right here. We have the option to power that with 5 volts or 3.3 volts. It's that simple, guys. It's an or selection. Use 5 volts or use 3.3 volts. You never solder bridge both of these at the same time. If you do, poof, the magic smoke will come out of your Arduino. Select which power source you're going to use. Like Gael, I've elected to use 5 volts on my analogs. And the reason I did that is because I'm going to be using the finger sensors on my robot, and I felt like having the 5 volts out there on those spongy fingertips would give me a better power source than trying to put 3.3 volts out there. It's an option, whichever way you want to go. If you're going to use these analog signals for other things, you may want the 3.3 volts on there. It's your choice. Select one and solder that gap right here. For 5 volts, you bridge this gap right here, and so 5 volts from this pin is now brought across here, and pardon me, what we have on this side, this point, this point, this point, this point, and this point are all electrically one connection. So if you put 5 volts here, you put 5 volts here, you put 5 volts here, you put 5 volts here. Alternately, if you put the 3.3 here, you put 3 volts here, 3 volts here, and 3 volts here. From this point, there's a path, a board path that comes from here, and it feeds down this side of the positive. All these are common. If you take a continuity meter and put it one end here and run down through here, you're going to get a beep on all of them. They're all tied common. Now, it gives you an option at this point. And it gives you a little flexibility if you've got the skill set to use it. Maybe you want just part of these as 3 volts. Maybe you want part of them as 5 volts. Maybe you're just going to use half of them. I don't know. But there's an option here. And this is that there's a split right here on this board. Okay? And we're going to look at the back side. And that split is right here. So if you want to power up both sides of that your analog signals, you solder this junction right here. And what that does is that this power is now passed to this point. And you've got power all the way down through here now. So now with the 5 volts jumper or the 3.3 volts jumper, whichever your option is, you get power from here to here to here, jumpered across to here, down to the A15, and then there's a solder link, a conductive path, I should say, on the board that sends that power to this point. And we're going to leave it at that point because that's the end of the analog circuit right there. We'll pick this point up again later, and I'll explain where we're going to use it. But whenever you put 5 volts or 3.3 volts, you end up with a conductive positive path all the way to this point. So this point is either going to be 5 volts or 3.3 volts. Okay? Let's continue on with the analog circuits now. This is just how to get power there, but we want to carry it a little bit further. The A reference. Okay? This is still to do with your analog circuits. On your A reference from the mega card, if you look, you'll see an A ref down here. Okay? That's passed up to our shield. That A ref is routed on the card, on the shield card, right here. You see it's, blow that up a little bit, see A ref is pointed right here. So you got a jumper point here where you can bring in the analog reference point. Now, what that means is that the Arduino card has a reference voltage that it compares all your analog inputs to. So whatever's coming in here on the signal gets compared to the analog reference. And when that way it can scale it for you. Okay, we're going to not get much deeper than that. Just know it's going to scale it. But the board has several ways of doing that. And if you just leave this unsoldered, it's going to use the internal reference, which is automatic, but it's 5 volts. Okay, so it's not a problem to leave it unsoldered if you elect to use 5 volts on your analog channel. If you're using 5 volts, it doesn't matter if you jumper this or not, because you're going to use the internal reference, which is 5 volts. Okay? But if you elect you want to use the 3.3 volts down here on your analog channel, So if you bridge this one and put 3.3 volts here, then you need to bridge this, right, and put that 3.3 volts onto the A reference pin, so that your internally the Arduino card knows that now it's going to use 3.3 volts as a reference. You also have to do a little changing in the script that you write for the Arduino. But I'm not going to carry this on. I got a guy that did an excellent job with this, so I'm just going to give you a reference to him. Right here on YouTube, if you go to this address, and I'll put that address in, down in my channel, so where you can pick it up, or you can just read it here and copy it over. Right? This comes from the Learn Electronics channel, and from what I gather, they've got several speakers, so that they introduce themselves in the videos. And so I really don't know if this is Bill or Bob or Tony who's speaking, but he'll introduce himself. He does an excellent job of showing you how to hook up that A reference pin right over here, and how to change it internally in the Arduino and what it does. And right here, he gives you some nice readouts, so you can see as he's turning his pot, you can see the readouts and how it's affected. So I'm not going to give you a lot of detail there. I'm just going to pop it up for a second.
Second time, because some dumbass, namely me, deleted all his project files for this, so instead of uploading them, so I have to do the video a second time. But that's cool because I like making videos for you guys. So
okay, so he's a nice, friendly guy. Speaks well. I hope you understand English. Okay. But around the world, we get pretty good translations on this stuff now. So let's leave that at that and pick up again where we were. Now the SIP resistor, this is optional. And it's optional, you need it only if you're going to use the sensors on the fingers. On the robot fingers, if you're going to use those, then you need this SIP resistor. If you don't plan on putting the sensors on the fingers, this goes away and you don't need to do this. This is the SIP resistor. SIP stands for Single Inline Package. You can compare that to a DIP, a dual inline package. A DIP, I think we're all familiar with. That's an IC chip. Where you got pins down both sides, so you got dual inline pins. Okay, this is a SIP, so it only has a single inline pin arrangement in the package. This is a prefab one that you can buy, which is the route I went. I bought them pre-made. This lower picture gives you an idea of what's happening inside that package if you buy it. Gael specifies that this has to be a type A SIP. A type A SIP tells you immediately that this is a bus arrangement. So this is the bus pin right here with no resistor on it. So this wire comes up and it's common across the top of all the resistors, forming the bus. And this bus is identified by the dot. So this is the bus end of a SIP. The other end are the individual resistors right here, this end of the resistors. Okay, now his little package is showing 9 resistors. You need only 7 resistors. Not a big deal. You could just clip this right here and cut 2 resistors off. It would work just fine. So that's kind of what's going on inside the SIP. Now, on the mini breakout board, we have to mount that SIP. And we mount it right here in this little rectangle right here. The bus, the one with the dot, the pin with the dot on it, goes in this square box right here. That's the positive voltage. So what we're doing is we're providing power to the bus right there. And here's our remaining resistor connections right here. Okay, so you just solder it in, and it sits between the power supply and the signal coming in from your individual finger sensors. We'll get into that a little bit right here. I'll kind of demonstrate that for you. So here you've got the 5 volts coming in to, on the bus of the SIP. And then the other end of the resistor is going to be tied to either one of the analogs, A0 through A15, on the analog card. Let's see if I've got that. Yeah, right here. Right? So here's the S. That into this S connection is tied in to this daughter board, or the mini breakout board, I should say, to these S connections. This represents the finger foam, this variable resistor, right? Because what we're dealing with is a piece of foam impregnated with carbon elements. And at rest, it's going to have a certain resistance value. It's going to be pretty high. And it can be even higher if you stretch it and pull it apart. You can even make less of those carbon elements touch each other. But we don't use it in that fashion. We use it in the opposite fashion. We use it so that his fingertip, as the robot grips something, he compresses that foam and tightens up all the foam particles so that more carbon elements within the foam touch, creating an electrical circuit. That's represented here by the variable resistor. So if I take this wiper, this represents how much we've compressed the foam. So at rest, this wiper would be moved all the way up to the top. So we've got the most resistance because the foam is expanded to its maximum value. That produces a higher voltage here. Hopefully somewhere near that 5 volt range will be produced here. Now, as the robot grips something, this wiper, represents the compression, will drop down closer to 0 or ground, so that we get a smaller amount of resistance being developed, and we get a smaller voltage here. Now, ideally, when it compressed all the way down, we would be all the way down here at ground, and we would see 0 volts here. That's never going to happen, right? Just by the nature of the foam, you're always going to have some resistive value in it. So internally, in the Arduino circuit, in the sketch in the Arduino program, we offset that by saying, okay, if, say, for example, maybe we pick 300. Any value 300 or less, we consider that the robot has completely gripped something. And on the high end, instead of 1024, we might say anything from 800 and higher, he's completely relaxed his finger and he's not touching anything. So we give it a little bit of a range there, just so you understand what's happening in the programming and what's going on. I hope I didn't confuse you too much with that. the PIR detector. Okay, this is the passive infrared detector, PIR. So I brought up the Mega again. There's actually no PIR terminal labeled here. Okay, but I brought this up because I discovered when I used my continuity checker that there's a 5 volt, see it labeled right here, 5 volts. These two pins are 5 volts. And let me move myself. These two pins down here are labeled ground. So I discovered this when I used my little continuity checker. And that became important on the shield, because I needed to get power. See, here's our PIR detector right here. And so we need our voltage here. Now, depending on the PIR you buy, it could be 3.3 volts or it could be 5 volts. So you need to be able to source this either way. Now, I'm going to tell you now, if you buy the recommended PIR sensor in his bill of materials, I contacted the company because they didn't provide a data sheet. So I contacted them and said, hey, what voltage does this PIR operate on? And they came back and they said, oh, it operates just fine on anything from 3 to 5 volts. So if you buy the recommended one, it'll run on either voltage, okay? And it will make its own correction internally and control its own voltage internally. Now, that becomes important because we have to now source that with the right voltage if you use a different sensor. So remember, when we did our analog channel here, we ran voltage up and down here, right? Right? And we could have selected 5 volts or 3.3 volts. So let's, for the sake of illustration, let's say we brought 3.3 volts. We soldered this bridge and we brought 3.3 volts down here. If you remember, I told you there was a trace, a board trace between here and this point. So I got 3.3 volts right here. When I did my continuity check, this bridge, the middle bridge point, continuity checks to here. When I continuity checked, I expected 5 volts here, so I put one lead here, and I went back to my 5 volts and got nothing. So I was a little surprised. And I did a little searching. That's when I discovered this point is continuity checked to this 5 volt point over here that I just pointed out to you from the Arduino Mega, right? And it's the only place on the board that this 5 volt connection is used. So there's continuity from this 5 volts to this point right here. The idea here now is that if you buy a 3.3 volt PIR detector, you could solder the bridge, you could bridge the gap here and you would get 3.3 volts, okay? If you use 3.3 volts for whatever reason on your analogs, but you bought a PIR detector with 5 volts, then you could solder across the other bridge and you could bring this 5 volts up to this point and properly power the PIR. Now, if you elected to use 5 volts for your analog channel and you ran 5 volts down here, this point's going to have 5 volts. This point's going to have 5 volts. So whichever way you bridged it, you're going to put 5 volts to the PIR. Using the recommended PIR detector, Doesn't matter. It can use 3.3 or it can use 5 volts because it will internally control its own voltage. But if you do buy a fixed voltage PIR detector from another source, know that the voltage on here may be only 5 volts, depending on what you elected to run on your analog channel. So if you use your analog channel at 5 volts and you happen to buy a PIR detector that requires 3.3 volts, then you can't jumper right here and get the proper voltage. You're going to have to improvise a little bit. Come up here and on this side solder, because you haven't bridged this because you're using 5 volts here, right? So with this unbridged, on this side, on the pin connector side, solder a wire. It can be a small, very small gauge wire, 26 gauge will be fine. Solder a wire here long enough to reach and solder to this middle point right here. Don't solder across these because they'll have 5 volts on them. So now you can improvise and you can get 3.3 volts using a wire down here. That will then be traced, wire traced on the board and provide your 3.3 volts up here for your PIR detector. Okay, I was a little amazed and hadn't realized that from reading the tutorial that PIR could be powered wrong, right? But again, it's not a problem if you buy everything off the recommended bill of material. You can run 3.5 volt for your 3.3 volt for your analog and power up your PIR right here as anticipated, or you can run 5 volts and then run a jumper. Okay, so that I was a little surprised to see that, but for me it helped to understand it. I hope I didn't totally confuse you on that one. LEDs, optional. Okay, and they're optional. Very few people will see them. Here's a completed board. With the LEDs mounted on it. Right, in the name of the robot InMove, he used blue LEDs. And again over here on this daughter board with 2 LEDs, he used blue in the name again. And down on the main shield, almost hard to see, are the 2 red LEDs that he used that were provided off the servo power. So let's take a look at what happens here. Now, if you look in the comments on his tutorial, on Gail's tutorial, and if you look on the form, and I cheated a little bit on the form, I did a search for 4700 or 470, right, and narrowed down the form search to find this. What he does in his bill of material, in his optional bill of material, he tells you you need the LEDs and you need the resistors, and he labels the resistors as 4700, 4700 ohm resistors, often referred to as 4.7K. So I looked, and sure enough on his board he's using 4700 ohm resistors. And I know the color code pretty well from memory. Yellow is 4, violet is 7. So I have 4, 7, and red is 2. And the third element always tells you how many zeros to add. So I have 4700, 4,700 ohm resistors, 4.7K. So he actually used 470K resistors. By the way, this band tells you the tolerance level, how accurate that resistor is. You don't have to worry with LEDs. Buy the cheapest ones. Now with 470 or 4.7K ohm resistors powering up these LEDs, I expected something very dim. And I think I'm actually seeing very dim LEDs. And I say that because whenever I put an LED under a camera, be it video or even a still camera, and try to show a video of something with an LED on it, the LED washes out the picture. They're bright enough that usually this picture here just, the whole area just gets washed out from the light being fed back into the lens of the camera. But here you can see I have nice crystal clear LEDs. So either he applied some very good filters to his camera equipment when he took this picture, or they're very dimly lit. And another reason I point that out is look at the LED, the body of the LED itself. You can even see the enlarged base around it. That LED is crystal clear, must be just barely illuminated. Even up here on the red ones, see there, you can still see a lot of the LED there. It's washed out a little bit more. You can see some of that red around it. And I can explain that in a little bit here. Okay, so that 4700 ohm resistor lights it up, but even he says, oops, maybe I should have used 470 ohm resistors. Let me back that back down. We're going to take a look at the board here and see how these resistors are being used, or LEDs are being used. On the board, on the main shield, in the word in move, he had these two blue LEDs right here. And he had his 4.7K resistor mounted right here. So I did a continuity check from this point to here and here, and they're common. Okay? And then I did a continuity check from ground to these 2 points, and they're common. So from this point to the resistor, remember this point I pointed out before, this is on a common trace. That trace travels all along here. So this is all one common area. So these LEDs can either be powered with 3.3 volts if you've elected to feed that 3.3 volts for your analog circuits. Remember that? Or if this common area could be powered with 5 volts depending on which of these you've selected. So these LEDs can be powered up with either 3.3 volts or 5 volts. Let's just hold on to that thought, okay? Now, on the board itself, he had 2 more LEDs that were red in color, just barely visible for us on the board, but they're there. Let's see how they're powered. Again, this point to ground gave me continuity. The resistor, oh, of course this is got continuity on it too, to the one side of the resistor. Okay, the resistor gets power from this power source. Okay, not from the 5 volts, not from the 3.3 volts up here, but it gets powered from servo power, not Arduino power. So this could be 6 volts, it could be 5 volts, it could be 7.2 volts, okay, depending on what power you're going to feed your servos. Now, I went over here to this LED and I did the same trace, right? This ground was to ground, which I expected. Trace between here gave me continuity. This resistor was powered from this power source. Now again, if you remember when we did the servo power, we may have jumpered all of these together. So these could all be the same voltage, or you could not jumper those, and these could be a different voltage for this LED. Just to let you know. Okay. Over here I looked, and there is no LED available for this power side. So if you were separating out your servos and running separate powers, you would have a power indication for this feed, you would have a power indication for this feed, but you would have no power indication for this feed. But with them all tied common, these two LEDs would be a good indication of servo power. So if they're lit and all your jumpers are commoned out, then you would know I have servo power. If this is lit, if these two blue are lit, you would know that you have power from the Arduino coming up. It's either 5 volts or 3.3 volts, but you know there's power on the Arduino, and it's coming up to the shield. Now, in addition to these, there's another set of blue LEDs. And let's see where they're powered from. On this daughter board, it mounts back onto the main shield. This is where you'll find the 2 additional blue LEDs that I showed you in the completed board. So where are they powered from? Well, this side of the resistor is common with continuity check, is common here. This side proved to be common to ground. I'll point that out here in a minute. But where does the resistor get its power from? The resistor, turns out there's a board trace from here to here. Now these 2 strings go down and mount to the main shield. So let's back up and see where they go. And if you look down here, here's where they're going to attach to, right here. Okay, so you've got your servo powers coming through here, right? Here's your plus and your minus. Remember, this power source fed these servos. This power source fed these servos. Okay, unless you jumpered, and then you know they're common. But there's servo power coming down here. Now, that servo power, that servo power also comes in here, this plus and this minus channel. Okay, plus and minus come up here. So right here on this end, these first 2 pins, this is plus and this is minus. So when I check for ground here, and I got continuity here. When I check for power, I got continuity from here to here. So the positive to here, through the resistor, out to the LEDs. So this could be whatever voltage you've got on your servos. It could be 6 volts, it could be 7.2 volts, right? Whatever you're powering with your servos. So know that these 2 red LEDs And these two blue LEDs on the daughter board are being powered by servo power, not by Arduino power, right? So you can, and I point this out to show you that this is why I said, whoops, this is the one I wanted to show you here. Okay, see, I said these aren't washed out at all, so they're at a low power source. This one here is beginning to wash out. See, you get the red filtering into the camera. That's because they're operating at a higher voltage than these, so they're brighter. And there's also another reason they're brighter. Let's back up to this one, okay? I've shown you that they're divided into two power sources, right? More than likely, well, he told us that he's using the 5 volts for his analogs. So these blue LEDs are being fed by 5 volts through a 4.7K resistor. He told us that all his servo powers have been jumpered, right? So that they're a common feed, and that he's using 6 volts for servo power. So these two red LEDs have got 6 volts on them. The daughter board, which is being fed up through this power source, is also on 6 volts. So I got a higher voltage here than I do here. So I get a brighter LED. But let's take a look a little bit at determining what else is at play. And again, somebody else did an excellent job at this, and I didn't feel like I needed to repeat it and create it myself. Let me just give credit where credit's due. Here I picked out Wikipedia, and all I did was type in typical LED voltage, you know, I Googled for it, and LED circuit, Wikipedia came up. So I went to it, and it gives you everything you ever wanted to know about LEDs. We're not going there, guys. All I want to do is point out here that it tells us typically on an LED, you're going to find you need a voltage somewhere between 1.8 and 3.3 volts. And why that range is explained. It goes on to say, look, a red LED typically needs somewhere between 1.7 and 2 volts. Remember, we had 2 red LEDs that were bright and beginning to wash out the camera a little bit, okay? And they also had a higher voltage than the blue LEDs, okay? And it goes on to say now, but the voltage drop varies based on the frequency of the light spectrum. So when you get out here to a blue color instead of red, you're on the far other end of the spectrum now. A blue LED typically drops somewhere from 3 to 3.3 volts. Okay, so let's go back here. If I had elected to use 3.3 volts right here on my analog channel, I would be feeding 3.3 volts to my blue LEDs, okay? And with a 4.7K ohm resistor, which you're going to see here in a minute, I'm not going to get much out of here. They're going to be extremely dim. With 3.3 volts, I just showed you from Wikipedia, basically I could put just a bare piece of wire across here and my blue LEDs would work fine. I wouldn't do it. I would put a little bit of a resistance in there just as a protection. Okay, even with 5 volts, I'm not going to need a very large resistor. So let's go back. Let me go to the next step on my illustration. So the red LEDs are going to use basically 2 volts. The blue LEDs need basically 3 volts, a little more than 3 volts. So how do I know what resistor to go in there? And this is where we're getting back into that back and forth in the form of, did I pick the right resistors, did I not? Okay, you can pick the resistor that meets your needs. I'm just going to show you a method of knowing how to do it. So I went back out onto the internet and I Googled for LED calculator, and I picked one out. Okay, and this is the one I happen to pick out. You can I highlight that. You can just Google LED calculators. You'll probably find this one right at the top of the list. That's where I found it, and it duplicates a little bit of what's going on in the Wikipedia page. You saw a little bit of these formulas, and it figures it all out for you. Here's the heart of the matter right here, this little electrical circuit. This voltage source, this is either going to be your servo power for your red LEDs, or this is going to be the voltage coming up from the Arduino Mega. So this could be 3.3 volts, this could be 5 volts. Or if you're using the red ones, this could be 6 volts or more, depending on what you're feeding to your servos. That's what that's representing. Okay, so you take that source voltage and you push it to an LED over here. Now LEDs are current sensitive devices, or current controlled devices. So it's the current that gives us what we want, not the voltage. Okay, so when you push current through an LED, the current causes the emission of light. Now, the typical milliamps that an LED requires is everybody says you can use 20 mils as a standard. That's the high end. That gives you the brightest LED. You can drop those milliamps, and dim that LED. And you do that by what resistor you select. So the more milliamps we put through that, the brighter the LED. The fewer milliamps we put through there, the dimmer the LED. And how do we control that? We do that with the resistor. Okay. The resistor gives us the limitation on the voltage. Okay. Remember, this LED, if it's red, it only needs 2 volts. But over here on the voltage source, we're giving it 6 volts. So the resistor has got to get rid of the extra voltage. It's got to get rid of the 4 volts we don't need. On the blue LEDs, this is 3.3 volts we need. We're either providing 3.3 volts or 5 volts. So that resistor needs to get rid of 0 volts or 1.7 volts, okay, or 2 volts. We'll call that 3 volts and 2 volts to get, to divide up that 5 volt power source. So that's basically what's happening in this circuit and what that resistor does for us, okay. We also size that resistor to limit the amount of current we want. So let's see how that's done. We don't have to be experts with this formula up here. He's doing that for us down here. He's made a nice simple little thing, fill in the blanks. Okay, first thing he says is give me the source voltage. Well, if you're doing the red LEDs, you're probably going to put in 6 because you're feeding servo voltage for the source. If you're doing the blue LEDs, well, actually one set of the blue is going to be on 6 too, isn't it? Okay, but if you're doing the main board, those blue LEDs on the main board, this is either going to be 5 volts or it's going to be 3.3 volts. Okay, so we're going to go with the 5 volt standard that most of us are going to use. So the blue LEDs on the main board are going to get 5 volts. The voltage drop to the LED, the Wikipedia told us, is 3.3 volts. Okay, the current we want through there will determine how bright that LED is going to be. Okay, we do that with the resistor. So he's already told us we want to put a resistor in there of 4,700 ohms. Okay, now look out here. He gives you ohms, kilo ohms, and everything, but just 4,700 ohms is good enough. Milliamps is what we expect to see back, so we leave that setting at milliamps. If we leave the current empty and say calculate, he's going to tell us how much current we're going to get. You can see we're going to get less than 1 milliamp of current through that LED. If 20 is max, 0.3 is pretty dim. Okay, that's why I think you can see the outline of that LED so clearly in that picture. Okay, so what if we put in kind of what everybody debated in the forums and said, oh, was that a mistake? Did you mean 470 ohms? And he came back and said, yeah, I probably need to learn to read color code better. So what if we put 470 ohms in there and zero out the current and calculate it? Now you see we're getting 3 mils through that blue LED. It's going to be a little bit brighter. Okay, what if I want it brighter? What if I wanted to really push the limits and I wanted to get 20 mils through there and make it as bright as I think I can make it without poof letting that magic smoke out? Okay, so this time I'm going to put I desire 20 mils. So what size resistor do I need? So I leave the resistor blank and I do a calculation. I only need an 85 ohm resistor to get full brightness out of that blue LED. Okay, but if I'm afraid I'm going to let that magic smoke out, let's change this a little bit. Let's say I only want it half bright. So we'll put 10 mils in and recalculate. I need a 170 ohm resistor. I kind of beat this horse to death, but I've given you a way you can determine your own resistor value to go in here. That's my goal. So I'm going to leave it at that. You can go to these pages. You know, you could use 180 ohm, you could use a 200 ohm as a standard and be done. Okay, but I just wanted to let you see how things are actually calculated and figured out. Let's get back over here. Ribbon cables. Moving on. Let's see what we can do with the ribbon cables. First and foremost, going through Gael's tutorial, he's constantly reminding us, do this right or you're going to burn things up. Do this right or you're going to burn things up. watch for where you put that red wire. Okay, it's important where you put that red wire. And why is that red wire important? Because that's the positive voltage source. Okay, these connectors are bringing positive and negative power out and then going to our sensors, our end devices where we're going to use that power, and they're coming back in to remain, the other pins. So we've got to get those corrected, done correctly, or we create short circuits. Okay. When the page gets translated, short circuits gets translated to shortcuts in English. But I think everybody understands pretty much what's going on. So let's look at this connector and how do we know how to use this connector. Well, the male side is the side that gets soldered into the mini breakout boards and the daughter boards. The male side has one side that has a notch cut out of it. We can see that right there. Okay. A side view, I was able to get a little clearer view. You can see that notch cut out. Okay. The purpose of the notch is so that you can't put the mating connector, the female end of the connector, you can't put it in any way but just one way. And that's accomplished right here. This is the female end with the ribbon cable on it. Looking down from the top of the connector, you can see that this side has a notched out portion here that protrudes out further. Okay. It also has two grooves, but we don't utilize them in this configuration. All we're interested in is the notch. Side view makes it a little harder to see. You can see the two grooves pretty clearly, but if you look close you can see the notch there. Let's not beat that to death. The opposite side of the connector, female connector, see here's the female end that drops down into the socket. That opposite side you can see is nice and smooth and flat. So there's a very clear distinction then. And here we're combining all three of them together. The male one that connects, that mounts into the board, there's the notch. Okay. The female that goes into it, here's the nice smooth side, and here's the side with the protruding alignment pin. In this picture, we're looking at the bottom side of the female connector. And we're looking at the top side of the male connector. Okay? So you can see that the alignment pin is on the opposite side from the notch. But if I try to connect these, what I would have to do is I'd have to take that female connector and I would have to turn it over, thus aligning the alignment pin with the notch, and then it would drop down in. But if I tried to reverse it, it wouldn't go in. So I think everybody can see that. You can pick one up and play with it. Oh yeah, pretty clear, pretty self-explanatory. So I beat that horse to death, but now I've got to get this male connector soldered onto the mini breakout boards. So how do I know that I've connected that correctly? Because I could just take it like it is, solder it. I could pick it up, I can turn it 180 degrees and insert it, and it'll go in. It'll solder in, and you'll think you're doing just fine. Well, the secret is the design of the breakout board. If you look at the breakout board, you see that this represents the male side of the connector. This rectangle represents the notch. Okay, so if you pick this straight up and set it straight in, this notch would fit right over this rectangle, and I know I've mounted it into the board correctly. Now, I guess while I'm here, I'm going to point out a little bit about the power too. The ribbon cable is 26 gauge wire. It won't carry much current without getting hot and burning and melting and destroying itself. So to overcome that, what you do is you use more than one wire. And that's what he's done in every one of his connectors. So you see this 1, 2, 3, 4. Those are all positive power leads. And then he uses 1, 2, 3, 4 for ground. And then the remainders he uses for the S, for the feedback signals. So we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? So these 6 are the electrically here. These 4 are electrically here. These 4 are electrically here. Does that make sense? Okay. Now, to help you with all this wiring, one of the users has made a spreadsheet to help us see all this. And again, I'm not going to reinvent the wheel. I'm just going to show you his spreadsheet. His spreadsheet is titled HE10. Okay, and I'm going to show you where to find this spreadsheet. And I cheated. I went up here and I said find HE10. Okay, and it scrolled down through the tutorial and showed it to me. And forgive me, I don't speak French, but here's the man's name that created this spreadsheet. Okay, and he gives you a link right here. Follow this link and you can go out and get this spreadsheet. I'll put it on my site as well, but I just want to give credit where credit's due. I did not create this spreadsheet. So let's go back and take a look at that spreadsheet. When you get his spreadsheet, this is what his is going to look like in French. So I took Google and I said, Google, translate this for me. And it comes back and it says female connecting wire for the hand, arm, stomach. All of them, he's looking at the female connectors. So then I studied it a little bit further, and also way down here at the bottom, he says the numbers, see here you got 26, 24, 22, 12, 13. The numbers correspond to pins on the Arduino card. So you can chase these electrical connections all the way back to the Arduino card and say if I got it in the right place with a continuity test. But how was he looking at this connector? Well, I took one and I played with it and I figured out he's looking at the bottom view of the connector. So I added in my spreadsheet, I said bottom view. Everybody's looking at the bottom view. And I added a couple more drawings to help us see that. Here was the drawing that we were just looking at. You can see the bottom view of the female connector. the top view of the male connector. So again, you would have to flip that over to plug it in. Okay, but the bottom view matches the schematic that he's drawn now for us in the spreadsheet. So how do we use that? Just as I was explaining, you can look here, you can see, right, he says 1, 2, 3, 4, 1, 2, 3, 4, that's power. And when you flip that over, whoops, I did that backwards. It's 1, 2, 3, 4. No, yeah, I'm 1, 2, 3, 4. And when you flip that over, then it's 1, 2, 3, 4. The positives fall in place. And 1, 2, 3, 4, the negatives fall in place. And then the opposite side, right down here, see there's only one positive, and then the numbers begin. So here's the positive. Here's 2, 3, 4, 5, 6, and 7. Okay, so all your negatives fall in place, all your positives fall in place, and all your signals, 2, 3, 4, 5, and 7 pin numbers, they align. So there's a good way to check out how everything falls in place. That helped me to understand and make sure I was clear. Okay, now let's take a look at the ribbon cable assembly. He has several more breakouts in his tutorial you can look at. He shows you one that was done poorly, one that was burning, a couple of different examples there. And he also goes on to show you where to mount these mini boards. I'm not going to do this. Pretty much going to stop right here after I explain this ribbon cable. So let's look at this other drawing over here where I've got my ribbon cable passed through. And how did I know how to do that? Again, I did it based on this, right? This female end. So I took it and I flipped it up, right side up. So now I'm looking at the top with the shield, right? And now I have to pass that ribbon cable in that gap. I couldn't show it here. You wouldn't be able to see the gap in it. When you pick one of those ribbon connectors up, you'll see the gap that I'm talking about. You pass it through, okay? And I exaggerated my pass through just so you could see it. Right? I came from the bottom of the picture up to the top of the picture, passed it through the top of the connector with the red lead on the side that had the power. Right? Remember, I just picked it up, flipped it over, and I knew. Now, I intend to cheat. I intend to make this even easier for me, right, to do. I'm going to go around, I'm going to mount all my male connector onto the mini boards, right, making sure I've got my notch aligned with the rectangle so that I know they're all mounted correctly. Then I'm going to take my male connectors, my female connector, right, I'm going to take it and I'm going to drop it down in because it will only drop in one way, right. When I do that, then I know the side that's got these two extra pins on it, right? That's my plus and that's my minus. And I know they're being fed from here, okay? And I'm gonna take my wife's fingernail polish or some red paint and I'm gonna swipe the male side and I'm gonna swipe the female side that's inserted there. And then I know this is where the red wire goes. I'm going to insert it in so that I match the red wire up. I probably should have done that in this video so you could have seen the idea. But I think you're getting the idea pretty clear. Get that in, get it lined up. You want to, of course, don't waste that much ribbon. Back it up so that the ribbon is just barely past the edge so that you know you're in good and deep. Squeeze that connector down, make your connection an electrical connection. Then you're going to take your ribbon and you're going to fold that ribbon back over the connector. Okay? Back over the connector. And then you're going to take the mechanical lockdown and you're going to insert it in these two notches. Push it down till it snaps. That's going to mechanically lock that cable. It does two things. It helps stabilize the electrical connection that you just pressed the copper connections into, and it's going to give you what they call a stress relief. So that when you pull against that cable, you pull against the mechanical action right here where this is binding that cable, right? So you pull against the cable and not against the pins that you're making the electrical connection with. So you don't loosen them and eventually cause an open circuit or even worse, a short between the wires. Okay. Another reason that I fold them back that direction is that the main length of the cable that's hanging down here is now hanging up here, right? And when I pick that connector up and drop it down into my male socket, my ribbon cable is now up here out of the way. And that lets me have access down here because I'm going to solder in my servo connect pins down here. You'll see them in the box. There wasn't much need to demonstrate that. They just drop in the hole. Okay, and they're 3-pin connectors for servos. Now Gail does point out to remind you that if you look at this board, let me see if I can blow that up. Go back here. Yeah, I can blow that up. If you look at the board, right, here's the servo, and you can tell they're servos because they've each got 3, right? You got negative power, positive power, and the signal coming back. So we know that's a servo. But over here on the side, he's got 2 extra pins, okay, where he's got power, positive power and negative power. When you cut that long strip of servo pins, make sure that you count and only cut it to the length of the servos. Don't cut an extra one because at first it's not going to fit in, right? And you don't need it. And you're going to run out of material. So he just tells you in his tutorial, catch that. Okay? Be sure you catch that. And if you catch that, once you fold that over, then you can get in and you can plug your servos in pretty easy, okay, to that connection. And you're not fighting the ribbon cable. Hope that makes sense to you. The ribbon cables are not that difficult. You just need to make sure you check out your polarities. Right? Make sure you get that red ribbon aligned right there, right? Make sure that's up there with that power. Okay? That pretty much covers everything that I had to say and do in this little video. So I hope it helps. I hope it takes some of the mystery out of that board, answers that question, why? Because I had to know. I just couldn't live with it. All right, guys. Have a good day. Enjoy your robot. And I'm going to close things down now. As soon as I find my F key, I move to a new computer for this. Hey guys, I know I ended this video, but I actually came back to edit it because I've now built my cards. So I just thought maybe I'd tag on to the end here some of the things I discovered while I was building my card. I basically, with the first one, I tried to follow step 1, step 2, step 3, and do everything the way he specified it. But I'd like to maybe make a couple of suggestions that might make yours easier, more convenient. So let me walk through what I discovered. He first has you start out here by, mounting the headers onto the shield, and then he moves on down and has you start doing the soldering in all your jumpers. Well, I did all this way with the first card, but I actually discovered that for me it was easier to go ahead and, before I put any of these headers on, while the card was nice and flat and easy to work with, I went ahead and I did all my jumper work first. I put my 5 volts here, I jumpered my 5 volts here, and I flipped the card over and I put the jumper in here, because he doesn't mention doing that jumper until much further down in. But I went ahead, flipped the card over and put the jumper on the back side here, and then I went and put the jumpers in for my servo power as well, and got all that done while the board was nice and flat. I went ahead and I put the reset button on, and I elected to do the LEDs. Not all of them, but I did elect to put the blue LEDs here in the in move. That way I knew I would have, when those were on, I knew I would have my 5 volts from the Arduino card. And I elected to put just one resistor in here. Since I have everything all jumpered together and only one power source, I used just one LED and resistor network to show that I had servo power, and I left it red in color just to make a distinction between the two power sources. So I did that. Now also remember, if you're going to put all the LEDs on, that there's a daughter board that mounts right in here that has a set on there. I would recommend that you put those on before you put the connector bases on as well. All that went well on the second card, nice and flat. One problem I discovered on the first card was right here on this video. Let me blow it up for you. He says, all right, flip it over. You put all the headers on the bottom side that going to mount the shield onto the Arduino. And now he says, flip it over, and on the top side, put all the headers in that are going to hold the daughter boards. So I did. I put all these headers in, just as you see on the picture here. Later, it caused me a problem. Okay, and what I discovered was I have to mount a daughter board right here on this one right here. See where my mouse is? And this was the problem. Okay, you got two cable bases soldered on here, and when you set that little daughter board down on that header, you can't get in to solder this. There's just no room to get in there to do it. So I struggled and fought with it, and finally I got that header back out of the motherboard, of the shield I should say, soldered it in here. Made this as a complete assembly first, right? Mounted everything to this and soldered this in. Then I set it back into the shield, flipped it over and soldered it from the bottom side. Not a problem at all. Unfortunately, I did that before I discovered another problem. Let me back up a slide here, and I'll show you what I'm talking about. Matter of fact, I'll do it right here on this bigger one. he has you put all these headers in for those daughter boards, which is fine. Notice right here on the PIR, he has no header on there. And I'll have to admit, when I was building it, I thought that's kind of odd, kind of weird. Right? Later, as I was doing the build, I discovered on this picture right here, there actually is a 3-pin header right here that he has you put on here. Okay, doesn't tell you about it, it just appears in this picture. So I cut a 3-pin header and tried to put it in there, it wouldn't fit. It wasn't that the header wouldn't fit the holes, the header physically wouldn't fit to align with the holes because of the edge of this daughter board. On the blue cards that you get now, this is not as clean a cut as you see here on this older card. There's a little overlap that hangs out past here, and it hangs out right over the edge of where that PIR connector's got to go. So with it already soldered in, you know, I got it to work. I had to file and use an X-Acto knife and carve and file and cut some of that extra daughter board away in order to get that header to drop down in like it should, and to know that I would have room to put the mating connector on it as well. So I would recommend that before you put this daughter board on, that you go ahead and put that PIR 3-pin header in there. Then when you once you've made this daughter board assembly, you can dry test it. Just drop it down in its sockets and see if you're going to have clearance on that PIR. If not, on my second card, it was so much easier to hold it up here in my hand and file it and clean it all up, you know, and get rid of all that overhang and drop it in and solder it. Those were the two main drawbacks that I saw to his assembly method. Another thing I would point out is just as a precaution, wasn't a problem, but I could see where it could be. These daughter boards, when you drop them onto those headers, if you press them all the way down so that the bottom of the daughter board sits on top of the black header, you can be compressing that far enough down that the solder traces on the back side of your connectors could actually be touching other solder traces on the main shield board. So before you solder your daughter boards in, take a peek underneath. Make sure you've got clearance between the daughter boards and the main shield board, and then solder it. It won't hurt to leave them raised up a little bit. You can see on his picture right here where my mouse is, this daughter board is actually sitting on top of that LED, and that's what stopped him from going all the way down. On mine, I had enough clearance to just clear that LED, and it would drop further down. And this doesn't seem to be as big a problem on the other daughter boards, but just be careful. So with that, let me close out again, say that it went well, it was a good build, the instructions are basically good, you can catch the little what ifs along the way. I just thought maybe I'd save you a little time, bring in awareness to the issues that I saw. Have a good day, and I'll say goodbye.